Okay. So first, DTFT. So as we said, there are 4 Fourier operations. Actually, the logic is very much similar. It's like you want to transform anything from time domain to frequency domain, and the other way back. You have the definition and the definition of the transformation and the inverse transformation, and you also have the table, pair table and property table. But something a little bit special about discrete time is like you don't have time t variable inside the equations. What you have is n variable. This is just the index. It's not time. It's nothing related to the actual time. You have index 0, 1, 2, or minus 10 integers, but they are not time. They're just the indexes. A result of this is the spectrum period is always 2 pi. So again, time domain, it does not have actual time, it just have indexes, and the result is the spectrum is always periodic, and the period is 2 pi. So I guess this is pretty easy. You're going to have two kind of problems, and one kind of problem is like you have some irregular shape like this, and the other is like you have exponentials, like homework problem 3 or 4, I guess. So for irregular shape, you use the definition. For the exponentials, you use one pair. So that pair is not on the final. It's not on this version of the cheat sheet, but I'm going to ask professor to add on the cheat sheet. So at least you have one pair for the DTFT. Yeah, because as you see here, DTFT does not have a table. It just has property. So I'm going to ask her to put at least one thing on the table. So then for the irregular shape, you use definition. So the definition is here. This is pretty clear. Well, again, by irregular shape, what I mean is it does not go from minus infinity to infinity. It has a clear cut. So like this one, because you see a u n minus 1 there. So u is like, well we see u n, u, I hate this. Thank you. Sorry for this. It's never as expected. Okay, let's see if it works. Okay. So okay, u n is one signal that is 1 when n is larger or equal to 0 and 0 otherwise. So when you n multiplies everything, the 0 is still the 0. So it has a clear cut that one part of the signal does not exist. So what we can have here is u n minus 1. Here we want to know when n minus 1 is 0. So that gives n equal to 0, equal to 1. So the non-zero error is n larger or equal to 1 and 0 otherwise. So that means we only have non-zero values of the signal x when n is larger or equal to 1. So we can have x e to the power of j omega equal to, as we said, n is larger or equal to 1, so n goes from 1 to infinity. X n here xn. So here we already know what xn is. Xn here is half to the power of n, and then we copy this part, e to the power of minus j omega n. So we are going to use geometric sum. Geometric sum is on your cheat sheet. It is here on your cheat sheet, first page. And so geometric sum is one thing about geometric sum is sum of geometric series is you have to start from 0. That's the thing. You cannot start from 1. But we have one thing start from 1 here. We have to change it. So that we can use another variable called like k equal to n minus 1, so that we can have k from 0 to infinity. So this will give us like k equal to 0 to infinity. So because k equal to n minus 1, so n equal to k plus 1. So we can have here is half to the power of k plus 1 and e to the power of minus j omega k plus 1. Because we know that a to the power of r times b to the power of r equal to ab together times the power of r to the power of r, right? So here is one k, here is another k. We can merge them together, right? So we will have k from 0 infinity half e to the power of minus j omega and half. Here is k plus 1. But here, this is not n plus 1, this is n, right? So we need to move that plus 1 out, right? So if there is no plus 1, if this one is not plus 1, then this means I have to time e to the power of minus j omega over 2. And we can move this term out. And the term here, well, we can use the geometric sum. This one equal to, well, let's keep the term here. E to the power of j minus j omega half and 1 minus 2e minus j omega. Yeah. So that's the answer. Question? Can you see that? I cannot scroll it. Sorry about that. So I'm going to upload this video. Yeah, if you cannot see it. Sorry about that. I try to have a. Can I scroll down? I will try to have a better app for this. Can I go like? Yeah, I think I can. Oh yeah, you see it? Did you see it? Okay. Question?
So when you were at the n equals 1 to infinity step, when you were at the n equals 1 to infinity step, so the second to last term, didn't you have added and subtracted when n equals 0? So basically just subtract.
Yeah, you can do that, but unless you do the simplification, you'll get multiple terms. Yeah. Actually, the answer is the same if you do the simplification. But if you, well, the question is, because this sum is from 1 to infinity, can I do from 0 to infinity and minus the n equal to 0 term? You can do that, and it's still a valid answer, but it will make your answer longer because you have two terms. If you do a simplification, they will be the same. But this will give you more concise answer. Okay, then let's go to the sampling theorem. It's like, wow, I always this channel, but this is not quizzed. Well, then there's a fight. So, as I said before, for sampling theorem problems, it is still a problem of Fourier transformation. So what are you going to do is, excuse me? So for sampling theorem, we are going to find two things. One is the sampling frequency. Fs, and S means sample, and the other is the maximum frequency Fm or F max, whatever you want. And sometimes there is one thing called the Nyquist sampling rate, and it's just twice the Fm. This is the Nyquist sampling rate. Yeah, but usually this one is given, or give you several and want you to compare, and then this one is something you want to find. So how to find this Fm? By the way, this should be Fs is larger than 2 Fm. So in the homework answer Professor gave you is like trying to compare the t's. Well, I suggest you not doing so because the theorem is saying F. Then try to compare everything F, and then it's more clear there. Yeah. So how to find Fm? Then you have to use Fourier transformation. Then you will get a spectrum, looks like whatever thing. Then you got the edges, one edge and the other edge. One is positive, the other is negative. Maybe W1 as omega 1 as C or omega. It's not necessarily minus omega 1, but usually it is given a minus omega 1, but let's say omega 2. So I want to find omega max to be, well, the maximum value of the absolute value of omega 1 and the absolute value of omega 2. See which one is longer. This side is longer or this side is longer, and take the longer one. Another thing I want to say is like, for Fourier transformation, sometimes you have F, sometimes you have omega equivalent, but you have different sets of the table. It's like in the cheat sheet that you're going to have in the finals, you have the tables in F, but you can have problems in omega, but I try to avoid that by telling Professor so. But in your task book, the tables are in omega. I want to say they are different tables, but they are equivalent. You can solve a real-world problem by either of the table, but try to be careful which one you're using. The usage is exactly the same. And yeah, again, first we find Fourier transformation, and then the spectrum of the continuous signal, and look both sides and see which edge is longer, and take the longer edge and take the absolute value and find the frequency. Okay. I'm trying to do one example here. So this is one modification from your homework problem. Yeah, as I said, you have to have the lookup table. Like one table, the table have one pair, this GT and this capital G omega, J omega. This is one pair. This is another pair. This is another pair. So you have the Fourier transformation of sinc function, cosine function, and sine function. Another thing, very good thing to know is like, well, sometimes you have the addition or summation of cosine and sines, but sometimes you have sine something over something. So whenever you see like sine t something over t, the thing come to your mind should be in the other domain, it is a square wave, center square wave. Yeah, this can be f, that means in time domain it's a square wave. So it can be scaled, like here scaled, here like shifted and scaled. It cannot be shifted, here scaled, but still in the other domain it should be a square wave. So in this case, without any computation, I should say capital X to omega should be a square wave. And by doing computation using this table, we're going to see that. Okay, so first, first let's do A. So by checking the table here, I got the Fourier transformation of cosine is like this. Can you see it clear? Like this is pi delta omega minus omega 0 plus delta omega plus omega 0. And there is only one parameter to know is what is omega 0 in this signal. So we just compare it. Yeah, we see it should be cosine something t, and that something is omega 0. So this cosine 2000 pi t, and the something is 2000 pi. This is omega 0 for the first problem. So then I can see the Fourier transformation of x1 t. Actually, curly braces better. Equal to this 4 times. Just use 4 times by linearity. So 4 times pi delta omega minus omega 0 is 2000 pi t. 2000 pi. So here is 2000 pi plus delta omega minus 2000 pi.
Is this supposed to be plus?
Supposed to be what?
Plus 2000. Yeah, it's plus 2000 for second term.
Oh, yeah. You're right. So, stylus. And if we try to plot this in frequency domain, and we see the only thing we care about are the shape of the delta functions. They are spikes, and they are shifted symmetrically by 2000 pi. Then it should look like, well, here is a spike, here is another spike, and this is minus 2000 pi, and it's 2000 pi here. And this is in frequency domain, we use omega here. And B, for B, we compare this signal with this signal. And we see the only thing we need to find is this WC. We see the cut-off frequency. So by comparing them, I see WC is 4,000 pi. Is WC. So the Fourier transformation of x2 t equal to, just copy this part and change this omega c into omega c, into this omega c. So equal to 1, because it's not scaled, because there is nothing here. Yeah, omega, absolute value of omega is less or equal to 4,000 pi, 0 otherwise. So we know this is square wave, right? And the boundary is here. Yeah, the boundary is here is 4,000 pi. So if we plot it, it will look like this. Minus 4,000 pi and 4000 pi. And this is omega x. So any question?
Okay, so what's the answer to the? It's asking for the Nyquist rate. So what would be the answer?
Yeah. Sorry about that. Yeah. So for the we found the Fourier transformation of this, right? So then by the spectrum we can look at the age on both sides. For the first graph, we see the age is here, right? So the maximum frequency is 2000 pi. So we see omega max, this is for A, omega max is 2000 pi. So the Nyquist rate omega and R is twice the maximum frequency is 4000 pi. Well, if the tables are given in omega, I think you're good here. But usually this does not make sense because you want to tune your sampler like real world sampler, like the machines you're going to use in labs. But here the machines are going to ask you what is the sample frequency then, and the unit is in hertz. So we can convert this angular frequency into the real frequencies in hertz. It's just by divided by 2 pi. So this is the same as 2000 hertz. But here, angular frequency is fine. And for B, this is the age. Because it's symmetric, I just look at one side. So for B, omega max is 4000 pi. So the frequency, Nyquist rate is twice it, so it's 8000 pi. And C. So C asks you to solve the Nyquist rate for this one. That means we want to find Fourier transformation of the product. And as we said before, usually if one of the signal is just the sine, cosine, or exponential, we can convert it into the frequency domain and find the convolution there, because in frequency domain, one of it will be spike, and here it is clear. This one is just the spikes, and this one has some shape, but we can find the convolution very easily by shifting this here and here, shifting left and right by 2000 pi. So first, let's write some equations. X3 j omega equal to x1 j omega convolute with x2 j omega. And we don't have to do any math here. We just do convolution by graph because we're shifting it, right? And actually we don't care about the shape of the result. We only care about the non-zero frequencies. So first one, if this is 0, first one will shift to the left by minus 2000 pi. If this is the center, then it will go here by 4000 pi. So here is minus 4000 pi minus 2000 pi. And it will go here by minus 2000 pi plus 4000 pi. Right, this is one side of the signal. The other side of signal will center at here, actually, because this is 2000 pi. And this one side will go here, the other side will go here. If you do the actual computation, here will be something higher because it adds up together. But we don't care about it. We only care about the, we only care about the non-zero frequency area. So let me move this up a little bit. so you guys can see. Okay, I guess you can see it now. So we only care what is the frequency here on the boundary. So this one is 2000 pi plus 4000 pi. So here is minus 4000 pi minus 2000 pi. Here is 2000 pi plus 4000 pi. So absolute value is the same. So omega m is 6000 pi. Let's write the answer down. And the Nyquist rate is double it is 12,000 pi. And in frequency is in hertz is 6,000 hertz. Right. Question?
Is it true for all cases that if we convolve two signals, the highest frequency will be the sum of their highest frequencies? Because here the sum of the highest frequency of this is the sum of the other.
Yeah, I should say yeah. I think it's right. But you better go through all this process in case the signal is not symmetric.
Okay.
Yeah, but usually the signal is symmetric, so you have a double, but not double.